Okay. Yeah, maybe let me just start with showing you guys the papers that I was referring to. So here, hmm. Yeah, so I saw some sort of social media content talking about this paper, and it's mentioning that they're training an AI, and then they want to train them to learn the causal reasoning. And yeah, so I thought it was interesting, so I sort of wanted to read it a little bit, but I don't quite understand it previously, which is why I feel like maybe it makes sense for me to understand what is the causal reasoning they were talking about firstly. And that was one of the citation of their paper. I think it's citation 11. It was a paper called Artificial Intelligence. No, it's called Axioms of Causal Relevance. So just look up this paper, and I read this paper, maybe half of it, read it maybe in more detail. And this paper is kind of more like a math paper, so it's easier for us to understand. So I'm going to present something about that paper, but also gonna explain a little bit. Wait, let me share my iPad now. Uh, uh, how to share my iPad?
So now it becomes a bit complicated for using the Zoom. So in the tab of the sharing, so there's a tab called Advanced, and once you click it, then there's a part of the iPhone, iPad, yeah, sharing.
I see. Yes, yes, I see it now. Wow, it's been a long time. Um, Yeah, I made a slides for it, but I made it using AI in the sense that I just told AI to maybe write definition one into a slide or something like that. And then I just wanted to see how AI can do this. And the slide, I
Antoine,
think,
we
what
want computer science talk, not a math talk. I'm just kidding.
I
I
really
I
love.
love slides. I love slides. I love slide talks.
cool, cool. And yeah, I'll try to make it accessible. So this is like axiomatic training. That's what they call. And so this, in my understanding, is like a lot of those AI models, they don't really understand causal things, like some kind of crazy things happens when you try to let a video generate. And there are previously there were like two approaches to maybe make the AI understand the causal reasoning behind things. And one was like you can incorporate those axioms as inductive biases. From my perspective, the way I see it is like you sort of when you teach the you teach a program to translate between two languages, you just teach the program the grammar. You just emphasize the grammar to the program. But from the development of maybe speech recognition or something, or AI translate, we sort of understand that this is very costly and very not useful. And then I think currently with the large language model being very popular, the idea of inferring things out of all of those passive data becomes sort of a mainstream thing. But then this can also be costly in the sense that when you think about the equations that's driving our physical world, the equation is so simple. But if you were to sort of infer that equation from all of those videos and pictures, then maybe you are using a large amount of data and to get something really, really small. And how to get something so accurate and so small from such large data can be costly or something. So that's my understanding. And now they're trying to propose something new, which is still using passive data in the sense that you're not teaching the program grammar kind of thing. You're not spending your time doing that. But so what are these passive data? So instead of maybe videos or pictures, now maybe those passive data are those axioms. Sort of you see sort of logic reasoning, but maybe presented in terms of graph. And those graphs, they are already there, and you sort of do a machine learning kind of thing, but use those graphs instead of using all those videos available. And so they do claim that by doing this, they allow generalization to complex structures in the sense that as compared with previous things, when you use the inductive bias, maybe you teach the programming grammar, like grammar 1, grammar 2, grammar 3, and then they don't know how to generalize it. So if you do the machine learning type of thing using the passive data about those axioms, then they can generalize it to complex structures of causal reasoning. Yeah. So yeah, the key advantage is sort of maybe less costly, but also gives a better result. And then the key finding here, these are about these are from the machine learning papers. So I just sort of skim over it, which is saying that the parameters numbers is supposed to be maybe small, but I don't have a feeling about that. And also, it can generalize to complex structures. And what are those complex structures? And it could be longer chains. Chains are sort of just causal reasoning chains. I'm going to show you some examples later. And then reversed orders, I don't really know what that is. Branch the graphs, maybe some type of causal reasoning graph. I don't know about that either. But the key thing is they can generalize to those complex structures, maybe without human teaching them. And they do claim that the performance is sort of on par with or even better than large language models like GPT or other stuff. Yeah, so yeah, these are the advantages in terms of the new idea that they have. And the future direction are also from the machine learning paper. Yeah, just sort of some kind of statements I don't fully understand. I just imagine that maybe it's going to help sort of maybe reduce hallucination type of thing. That's just my general understanding, but also not costly. And yeah, now I jump to the other paper, which is the very old paper about the causal relevance. And in general, this paper is talking about some sort of things like if you have a graph of some sort of causal relation, and they're talking about whether one thing depends on the other thing or not. And they do talk about the probabilistic type of dependence and also the deterministic type of dependence. And also here they emphasize something which was unfamiliar to me. It's like if I show you a graph, yeah, something like this, and something like here you have u1, and then it sort of affects x, and then eventually there's y, but u1 affects y, and x also affects y. So this is one of a graph that they were talking about. And in this paper, what they emphasize a lot is they would want to change one of those variables, sort of change it by hand. You sort of set it to something. And then think about how it affects the value of y. So, and as compared to this, there's another thing, which is if you find out the value of x is 1, find x equals 1. Then you ask the question about what is the probability of y. Yeah, that is another type of thing. So in this paper, they focus a lot on changing things by hand, right? I just want to say that in advance. And then, yeah, so this paper, they claim that they develop axioms, but for me, that those axioms sound like theorems. So I would say there's more or less theorems. So it's like they prove theorems for things like X is causally irrelevant to Y in the context of another variable Z sort of thing. And here the contrast between causal and informational irrelevance was the thing that I mentioned before, which was like if you find X to be 1, ask about the probability of Y, then that's the informational. And as in this paper, they set X equal to 1 and ask about the probability of Y, how is it impacted? And that's the causal part, which is the main focus of this paper. Yeah, and as I mentioned before, there's the probability and this deterministic both. They're going to talk about it. But today I'll only talk about the probabilistic part. Yep. And yeah, so here, yeah, they mentioned that in the probabilistic setting, I believe what they're saying is like if you don't assume further assumptions, you can only prove 2 theorems. And so I'm going to show you the 2 theorems at the end of it. Yeah. Yeah. And then for a deterministic type, yeah, they can prove a lot more theorems in this setting. So I haven't read the deterministic part, so I can't explain why they can prove a lot more theorems. Yep. And here, to begin with, there's the definition of a causal model, which is the main focus of the paper. And here they said that there are 3 tuples. There's a V and U and F. And V is, they call the set of endogenous variables. And U is what they call the exogenous variables. And then here F would be some sort of function that help you determine V. Most importantly, help you determine V, but then based on the value of things from U and also other things in V. So we mainly think of U as those things that you cannot change. You don't get to say anything about things in U, but those things in U can change things in V, and but things in V you can change them. Like what I mentioned before, set X equals 1, you can do that. And here you should think of V and U as set of variables. So V is like a set that contains maybe X or Y or Z. And then U is a set that contains things like V1, V2, maybe U1, U2, U1 and U2, and maybe W sometimes. Yeah, just think of them as sets. Each set contains those variables. And for each X, X is a variable, but also you can think of like the lowercase x. So a lot of the times, those variables are just binary, so they can actually they can equal to 0 or X equals 1. Yeah, sort of like that. That's for each variable. And yeah, I wanted to show you this example sort of right after the definition. And here we have the, in this case, we have V equals X and Y. And the U is contains only the variable U1 here. And we also have the function available here in the sense that they're saying that X equals U1. So that's just very simple. Whatever U1 is, X equals that. And then Y is 1. if x equals u1 and if x does not equal to u1, y equal to 0. So that's also very simple. And also here we mentioned that all of these variables are binary, so they're either 0 or 1. And also this model is probabilistic in the sense that there's a probability about u that is given. Yep. And here you can imagine a lot of different things like, for example, you can ask the question of what is the probability of y equals 1? And just because x equals u1 and x always equal to u1, so y is always 1. So the probability of u1 actually does not affect the probability of y. So here you get this is actually just 1. It's always 1. And then the probability of y equals 0, as you can imagine, is 0. Yeah, just because x always equals u1. There's always not an otherwise thing happen. But this example is still pretty interesting in the sense that it's sort of it becomes interesting when you set x equal to something. As I mentioned before, this paper care a lot about setting variables to things. So if you set x equals 1, then you can ask similar questions about p of y equals to 1. But then here it's important that we set x equals 1. They use the notation, I believe, to do x equals 1. Yeah. So you can ask questions like this. And now, just because x equals 1, when you do this, this means that whatever equation about x will be affected in the sense that this will be just replaced by x equals 1. And then, but the equation here will not be affected. So when you do that, then you get things like x equals 1, and then y is the value of y really depends on the value of u1 now. So here they mentioned that the probability of u1 is 0.5, meaning that there's a 0.5 chance for u1 to be 0 and 0.5 chance for u1 to be 1. So you consider if u1 equals 0, then you have x equals 1 and u1 equals 0, so u1 does not equal to x, right? So in this case, then y equals 0, and if u1 equals 1, then y equals 1, just because in this case u1 actually equals y. So now if you ask a similar question like this, then the probability of y equals 1 when you set x equal to 1 will be just 0.5. And similarly, we could calculate that the probability of y equal to 0 when you set x equals 1 is also 0.5. Yeah. So yeah, this is an example of a graph, and then they care a lot about the things like set some variable equal to something. And the formal language of what I'm talking about, like setting some variable equal to something, is called, to begin with, there is the language of submodel. Yeah, let me start here. Submodel, which is just to begin with a model, and then you sort of replace all the equation for a variable x by setting it equal to a specific value of the output of x. Yeah. And the way they represent it is they say this is intervention, or they use the notation of do x equal to something. Right. So this is what I've been talking about, like set x equals 1. This is what they call a submodel or intervention. And yeah, the effect of action is another notation that they've been using, which is just setting x equal to a specific value and give you a submodel m of x. So the submodel is referring to this m of x, and then the effect of action may be referred to the action of choosing x equal to something. And the related response of y is when you set x equal to something, you should be able to find the value of y, in the sense that in a lot of the models, there is actually unique solution of this equation f. So this is saying that if you set the x variable to be this specific value for x, and then all those u values are given, you should be able to solve for the y value, right? And those are the what they call the potential response of y. Yep. And yeah, I think the counterfactual is another notation that they use, which is related to the potential response. But I don't see the subtle difference between definition 4 and 5 yet. Yeah. Yeah. I would say that it's just this statement, you should interpret it as talking about the potential response like this. Yeah.
Yeah, it seems like just fix the capital U, which was the random one, to be just some fixed like the value. I mean, for the interpretation, I don't know.
Oh, you mean fixed
Or U, yeah.
capital U to be lowercase u?
Yeah, so
That-
it seems like the capital U stands for the random variable, and small u might just, I mean, maybe just treat for a moment as just a deterministic. So it seems that might be wrong.
It could be. I am not sure. Yeah.
You mean U is an event of the capital V, U.
Yeah. Yeah. I would say they're calling this the potential response. So, yeah, I think it was me who caused this problem. I think it's supposed to be lowercase u here as well. Yeah, I am double checking with the paper, and that was the correct notation, I think. But you're right, the lowercase u's, they normally use to represent one incident of it, and then the capital U is sort of just the variable. Yeah. And then there's the probabilistic causal model, which is like you have a causal model, and then you also have the probability of things. But here, normally they only assign the probability of things that is in the set U. They don't assign the probability of things in the set of V, which is like X or Y. But just because of those equations, you should be able to solve for X or Y or Z, and then you get the probability of X, Y, or Z as a consequence. Yeah. Yeah, so here, key point is that they define the probability distribution of those endogenous variable and enables computation of counterfactual probabilities, which was things like y of x of u kind of things. Yep, and these are the variables in the set u. Yep. And then here's the very important definition here in the probabilistic causal probability part, which is they're saying that the X is causally irrelevant, but probabilistically causally relevant to Y, and given the variable Z, and they write it like X does not imply Y given Z. Something like this. And the way they defined it is you choose any incidence X, X prime, and Y, and Z, then the probability of Y when Z is set to this incident Z. So the notation here should be understood in terms of do Z equals Z. Yep. And then X hat means what they call the intervention, like do X equals X. Yep. So if you calculate these type of probabilities, there are probabilities of Y when X and the Z are set to be a specific value. And also in particular, they would want to set X to be different values, like X and X prime. And if you find that the probability of Y is the same, no matter which value you set X equal to, then you say that X is causally relevant to Y, but probabilistically causally relevant to Y given Z. And here, the set X and Y and the Z, they can be one variable, but they can also be two variable, or they can be empty set. So I found it confusing when I was reading it the first time. Yeah, so that's the definition here. And yeah, so the interpretation is pretty standard in the sense that you fix Z, and changing X between the possible outcomes of X does not change the probability of Y. Yep, that's the interpretation of it. And with this, there is the interesting thing. Normally, when you think in terms of probability, you think of the probability of Y, and then you think of the probability of Y when X is found to be certain value. So here, think of it as X is found to be 1 instead of X is said to be 1. And normally, if you take the maximum over all possible outcomes of X, then the probability is supposed to be larger than the probability of Y. Yeah. And similarly, when you take the minimum over all possible value of X, then this is supposed to be less than or equal to P of Y. It is good to share the definition of conditional expectation and conditional probability.
Yeah, I just wanted to just make the comment that so these are all about the conditional probability. So if some of you want to just share the very precise mathematical definitions and the intuition, I can just simply share. So that's just I want to just put it.
Yeah, I think I am interested in that, but I am a little bit worried that if we pursue this direction, then it could be different from what you expected, like the Olivier curvature type of direction.
Yeah, it's not a big deal. So I can just present in just 10 to just 20 minutes later on. So whenever we just want to just discuss for that. Yeah, it's not a big deal.
Okay, yeah, I'm definitely very interested. Yeah, so here, yeah, I think this is sort of what you expect to hold when you're talking about, I think this is the conditional probability that you mentioned. Yeah. and also they call it the informational relevance, which is not the main focus of this paper, but the other type of causal relevance. And then this inequality does not hold for the causal relevance, which is the main focus of this paper. When you set the variable of x equal to certain things and you find the probability of y, when you try to do that, then the equation 14 here can be violated. Yeah, so P of y can be greater than the maximum. It can also be less than the minimum. I think I want to show you this by figure 5, which is the example that I showed before. And this example can show you that in terms of the causal relevance, they can violate the inequality 14. So here, as I mentioned, if you don't do the intervention, you don't change x at all, by the equation x is supposed to equal to u1. So x always equals u1 and y is always 1. So if you ask what is P of y, then P of y is when y equals 1, P of y is always 1. And P of y, when y equals 0, is always 0. So these are simple because the equation said so. And then you ask the question of P of y equals 1 when I do the intervention like x equals 1. And as I calculated before, this was supposed to be 0.5. And similarly, we also calculated y equals 1. What is the probability for y to be equal to 1? For y to be equal to 0 when I set the value of x equals 1. This is going to be 0.5 as well. And it should be reasonable to believe that if I do the same thing of setting x equals 0 and ask what is the probability of y equal to 1, this is also 0.5. And then you ask the question of what is the probability for y to be 0 when you set x equal to 0. Then again, this is 0.5. So now if you ask the question of what is the maximum over x, but the probability of y equals 1, and then do x equals certain thing is this notation of fixing the x value to be something. This is sort of an intervention. And you ask this question, then as you can see that this is 0.5. Now the maximum over all possible x is 0.5, but the probability of y equal to 1 is 1. Yep. So this was, I would say, a little bit surprising in terms of the causal relevance that they talk about. Yep. Yeah, and which also make figure 5 a very interesting example. Yep. And here's the statement of the theorem. They call it the axiom, but in the paper they also say that that's a theorem. So I would say that's a theorem. I'll state the theorem and you can decide whether it's axiom or theorem. So they said that for any causal model, the following two properties must hold. This is for, I believe this is for probabilistic causal model. Yeah, so this notation is only defined in terms of probabilistic causal model. first of all, the right decomposition, which is if you have x does not determine y and w, which is like two, you can think of it as two sets or two variables, given z. If you have this, then this actually implies that x does not determine y and x does not determine w, both given z. So you can prove an statement here. And another statement is, right, here is just some interpretation of this theorem. And another theorem is called the right intersection, which is saying that if you can prove that given z and w fixed, x does not, y is not determined by x, and at the same time you can prove that given z and x fixed, then y is not determined by w, then you can prove that if only z is given and y does not depend on x and w. Right. So these are the only two theorems that they can prove. And before we talk about a proof, there are a lot of, this is 2.2. Yeah. Yeah. There are a lot of these type of sort of implications, but they're wrong. And they can construct counterexample for each one of them. So all of these things are wrong. So if you feel like the previous two theorems are natural or easy to come up with, then these sort of show you that there are a lot of traps that you could fall into. Right. Yeah. Yeah, so here's a comment about those counterexamples. These properties in the previous slide, they may seem intuitive, but do not hold for all causal model. And the paper gave counterexamples for each property. Only checked one, but they mentioned that they have for everyone. Yeah, so now let's let me talk about the proof a little bit. Let me see if I remember. So for the first one, the way the probability, the irrelevance, causal irrelevance is defined is that the first one is if you have x and x prime and then z, y, and w, all of them given, and you should be able to get that p of y and w when you fix z, and then when you fix x equals p of y and w, when you fix z, but you fix x to be another value, which is x prime. So this is what we start with. This is the proposition that we start with. Let's see how to prove this one. The proof is very simple. Let me see. I think you're basically supposed to sum over all the value for, wait, where's w? Oh, w is here. Okay, so basically you sum over w and that's it. Yeah. So and because of this, you can change z, you can change x to be x prime, and for no matter what y value that you choose, you get that you get P of y and z hat x hat equals P of y z hat and x hat prime. So which is the definition of this proposition over here. Yeah. So the proof of these theorems are really simple. So you just basically sum over things, and that's gonna work. Yeah. And yeah, let me just finish by demonstrating why this does not work. Let's see. Yeah. Maybe it's going to be so to begin with, we can show that y does not work by using this example here. This is figure 6 from the paper. Let's see. We need to show that to begin with, x is x and w. We need to show that this is true. So here, as I mentioned before, you can take those notation like z to be a set or the empty set. And here, in order to show that this is a counterexample, they took z to be the empty set. So let's show that this is the case. So we're supposed to see that P for all x and w, and also x prime, w prime, and for all y value, and z is supposed to be an empty set. We have P of y when x and w are fixed equals P of y when x and w fixed to be another value. So we need to show that this is the case. And here, the variable y is here, and it's all of the variables here are again binary, so they're either 0 or 1. And here y depends on the value of x and w and u1. The way you determine it is you add up the 3 numbers and you look at the parity of that number, so it's either 0 or 1 again. So here, if you take x equals 1 and w equals 1, then we calculate P of y when you have this is 1 and this is 1. Then this is the parity of x plus w plus u1. So you get, this is the parity of 1 plus 1 plus u1. And u1 can be 0 or 1 with a probability of 0.5 being 0, 0.5 being 1. So that when u1 is 1, then this is an odd number, so the parity is 1. When u1 is even number, this is an even number, and it will be 0. So so the result of y entirely depends on what is u1. So here you can get this is 0.5, and this is for y equals 1, and then also 0.5 for y equals 0. Yep. And similarly, we can calculate other possibilities like P of y when you set one of them equal to 1 and the other one equal to 0. And that is looking at the parity of 0 plus 1 plus u1. So now again, this number depends on U1. When U1 is 1, you get 0. When U1 is 0, you get 1. So the result here is still the same, 0.5, 0.5, and as you can imagine, for 0 and 1 here, the result is the same because x and w are sort of the same thing. And the last thing is p of y. When you fix both of them equal to 0, then you get, this is like the parity of 0 plus 0 plus u1. So again, it depends on the outcome of u1. So when u1 is 1, y is 1. u1 is 0, y is 0. Yeah. So that's the all the probability in this case. And as we can see that it really does not depend on x or w, right? Because the probability is the same no matter what you set x or w equal to. Right. Now let's see that it does not satisfy either of these two results. Let me write it here. So we need to show that it violates this thing. And again, we set z equal to empty set. So we need to look at for any x and x prime and also y, and keep in mind that z equals the empty set. So for any x and x prime, we need to show that the probability of y can change. So p of y, when we set x equal to 0, then that's about the, now w is determined by the original equation, so w is equal to x, and the equation of x does not work, so that now we are looking at the parity of 0 plus w, since w equals x, so we know that w is 0 as well, and plus u1. So because of this, we calculate that the result of y depends on u1. It could be either 1 or 0. Either case have probability of 0.5. And if we look at p of y when x is set to be 1, then we have the parity. Wait, why are they the same? X. When x is set to be 1, then we have, this is the parity of 1 plus w equals x, 1 plus 1 plus u1. So
It seems the same.
what thing?
It seems the same as 0 plus 0 plus u1, right?
Yeah, that's not good. Yeah, maybe
What
I
happened?
made a mistake somewhere.
Mm,
Let me see the figure 6. Yeah, I thought it makes perfect sense previously. Oh, I wrote it wrong. Yeah, I think that is the typo created by AI when I use AI to transfer the graph from the paper. So the paper actually has this equation of w equals u1.
oh, I see. Okay.
Yep. Yeah, so and AI made a mistake and I did not catch it. So w equals u1 when we do that, then yeah, it doesn't matter for the previous argument, just because previously both of these, we ignored both of these equations because we set x and w to equal to a specific value. Now we don't have, we still have the equation for w working, so that this is going to be w equals u1. So in the case when you set x equal to 0, then u1 adding u1 is always always even. Either u1 is 1 or 0, which is why you always get this is going to be 1. Wait. The probability of, wait, the notation is a little bit weird. Okay, did I? Yeah, it's supposed to be 0.5. Okay, this is 1 is like y equal to 0, because this is always an even number. And this is y equals 1. It never happens. And if you set the variable x equal to 1, then you get the parity of 1 adding u1 adding u1. And now because this is odd, so it's always odd, because this is even. So again, it can equal to 1 or 0, but here is for y equal to 1. And here is for y equal to 0. Yeah, so now it's switched. And if you calculate the other one, you get similar thing because x and w are sort of the same. Right, so again, this example is interesting because it is a counterexample of something that may seem intuitive. You may expect this to be a theorem that you could prove, but this is an example to show you that no, it's not true. Yeah, I'll just stop here.
Yeah, this is very, very interesting. Yeah.
Yeah, this is more like the math that we know.
And one thing I want to point out on the reference paper that you share. So it seems this is nothing to do with the transformer, even though they uses the transformer to just to check their like the experiment. But so the definitions and the causal models that you introduced today, so they just use the transformer. What I just thought last time of last conversation was that there's actually various versions of the different types of transformer with some geometric version as well, so that if one simply just replace the transformer, for example, such as the hyperbolic transformer, for example, then one might take some benefit for that, but seems that's not the core of this like the approach. So it's about the understanding causal model, and yeah, seems very interesting. Yeah, thanks for sharing.
Yeah, yeah, I understand that it's not very relevant, but I think the causal thing that they're talking about maybe has other, maybe can be useful in other ways or something like that.
Yeah.
Oh, and also, as I mentioned to you the last time, that one of the authors is a Turing Prize winner, Turing Award winner. Yeah, so they're a big guy.
Yep. So seems in any perspective seems interesting. So if Karen has no like the strong opinion or the feedback, then so it seems I think from today's calculations, though this is all about the calculation of the conditional probability and try to compare with the original probability, and we intuitively know what those are. But if you guys don't mind, then may I just introduce the definition in just 10 minutes so that we just keep the the familiar, comfortable definition as mathematicians. How about
Yeah, I like probability now. I'm reading it about it a little bit. So yeah, it's good. Let's go over it.
Yeah, so I think it could be beneficial. So let me share my screen. So this is one of the notes that I first, when I studied the probability side in the reverse May, so this is one of the node, but those contexts are very like the universal, so you can find it in like any references that when you try to find the probability like the references. So what I wanna share is about the definition of the conditional expectation and the conditional probability. So we studied the measure theory before. So what I want to assume is the Radon-Nikodym theorem, which is a big theorem for the applied side, but we know what those are. So let me just try to remind you, assuming you already know it, but I just want to see the statement just together, just simply that's it. So we start from the measurable space. So I assume we are all familiar with these definitions, right? So given the measurable space, and we give two sigma finite measures on it, and we assume they are absolutely like the continuous with respect to each other. So that if this measure is 0 with some like the Borel set, then the corresponding new measure at that set should be 0. We know what each mean here should be. Then we are actually able to represent this measure nu in terms of mu with some Aron function. And there's just a unique such a Aron function, and we call such a H the Radon-Nikodym derivative. That's the Radon-Nikodym theorem states for. Are you all okay with it? So I just want to start with this statement, which is very like the abstract for the apply like the people, but for us, it's okay. So I just want to start from here. So is it okay for all of us? All right. So now let's jump into the definition of the conditional expectation. I mean, rigorously. So what we will start with is the setting of the probability state. So let's just look at it each of one. So this sigma, let me say omega. Omega and F just stands for the measurable space. We all know what that is. And we just put the real probability measure, meaning that this is just a measure, and the total measure should be equal to 1. It could be just a change of like such as a complex measure or whatsoever, but we just require the condition of this P to be the probability measure. And in general, this would be just a measure space with just one additional condition over here. Are you with me? That's we call the probability space. So it's very clear, mathematically speaking. And we call usually this omega by the sample space, in my opinion. And this F has two different names. In measure theory, we are all familiar with the name of the sigma algebra, because sigma stands for the countable additivity. We all know what those are. But this F usually stands for the sigma field in probability theory. Those are mathematically exactly the same, but they just use the different terminology and the name on it. So this F, let me use either the sigma field or sigma algebra, whatever. We all know what those are. So in order to define the conditional expectation, we just fix the sub-sigma algebra. So let me just call this G by just a G. So this G is the sub-sigma algebra inside of this F. Everything is very clear. And the terminology of the random variables does nothing but the measurable function. We know what measurable function is, so that we start from the Borel set in the codomain, and the inverse image should belong to this set. We usually just consider the event as just the inside of the Borel sigma algebra, but there could be just a variation of the measure functions. But let's just use the most familiar one, so that the terminology of the random variable is just nothing but the measure function. It's very also clear. And we just assume, so usually this measure function is just L1 in general. It's just some reasonable assumption, just putting some just a reasonable assumption to deal with the abstract integration. And with this setting up to here, so that we have a probability space, and we fix the sub-sigma algebra, and we fix the 1L1 function. In such a case, what we should do is that then we are able to create another measure, because we already fixed the measure P here, we already fixed the measure P here, and we already have the measure function, so that by just assigning each just the element, but instead of from F, but this G, so that the right-hand side should be interpreted as a measure defined on G. Are you with me? So that we just define the measure by using the abstract integral that we should be able to define, because we start from just the Aron function. Then now we can apply the Radon-Nikodym theorem, so that we know that in such a case, there exists a unique Aron function that makes this equality happens. And we call such a Y is the Radon-Nikodym derivative. That's what Radon-Nikodym theorem states for. So the procedure mathematically defined is that we fix probability space with the sigma sub-sigma field.
What is the difference between X and Y? If you write it
The
this
reason
way,
is the following. So this X is, we start from the random variable defined on this F. meaning that if we just fix any Borel set, the inverse image should belong to this set. Because this random variable just means the measurable function as a definition, so that each inverse image of Borel set should belong to this F. But now we fix this another sigma algebra F. This can be F, but we don't care. We just fix the arbitrary sub sigma algebra, this G here. Then by using this L1 measurable function, then we use this right-hand side as a definition of the one measure defined on this measurable space. This measurable space with this G. And with this measure, we want to use the Radon equivalent theorem to induce this Y. So this Y depends on choices of this sub-sigma algebra. So that what you can see is if we choose this G to be exactly F, then this Y should be equal to X. There's no other choices. But because of this presence of G, this Y depends on the measure because measure is defined on G, not F. So the corresponding Y depends on choices of the sub-sigma algebra. Is that okay with all of us? So that such a random variable, we will call the conditional expectation of X with respect to the sub-sigma field G. This is a definition. So that we usually denote the conditional expectation mathematically by this notation. So that if you just compare with the Ventrans, the very intuitive calculation of the conditional probability, so it seems not exactly coincide in the notation in a sense that we usually plug in this slot for the sub-sigma field instead of putting some values. So that we need to justify why that intuitive, like the way of calculating makes sense in terms of this definition. But again, mathematically speaking, we always define 100% the conditional expectation by this description in terms of the Radon equivalent theorem. So let me first give you the definition of the conditional expectation rigorously and try to interpret this with just apply like the way. So are these all okay with all of you, by the way?
Just a little bit worried that I've been mentioning there's informational, causal, irrelevance, and then there's an intervention type of, which one is this? What do you think?
So what you use is, so for example, you did the lots of the calculations such as this type of the things, right? This type of the things, basically. So in order to describe either cases, so I just wanna say, so either the conditional expectation or conditional probability in any cases would be defined by using this object, which is the random variable. So keep this like the mathematical definition in our mind, in a sense that the conditional expectation is not exactly the value. So this is about the measurable function. I mean, the mathematical definition itself. Yeah, this is our starting point. So it becomes quite confusing because our intuition is a bit slightly different from this description. So that I need to justify why this exactly actually coincides with what we saw.
I want to say that if we choose like omega to be a set, like with 2 points, then can you get what I was talking about?
Yeah. So let me just give that example to see why they are indeed relevant. So let me just jump into that. So for example, so let's just look at this example together. Okay. So that we fix one, let me just say Borel set, just one Borel set with assigning some probability value between 0 and 1. So this is just a reasonable assumption. We just exclude that as a trivial case, either the probability is equal to 0 or 1. So just choose some probability, just the value for this Borel set. Is that okay for the setting? Then what we will do is we will consider the smallest possible sigma algebra containing this B. Then we know that there are only just of those 4 sets in order to make it to be a sigma algebra. So there must be the ambient set, there must be the complement, and there must be the empty set. And these are all like the at least necessary like the elements in for this sigma algebra that contains this B, and this must be the smallest one containing this B. So that we now create the sub-sigma field inside of this F, whatever F was actually given. Is that okay? So that what we want to do is we'd like to calculate the following notation. So here's the notation. So when we use this notation, now this sub-sigma field, sub-sigma algebra G is now specified. Just this is the collection of those 4 elements here. And this notation is defined by using this one. So let me also be clear. So that we fix also one element, we usually call it by the event inside of this F. So we fix the event, and this is either the indicator function in probabilistic, like the term, or the characteristic function. If we just look at the measure theory, okay, right? Given the set B, set A, then if the element is chosen from this A, then we just put the value equal to 1, otherwise equal to 0. So it's just either called by the characteristic function or just the indicator function. Those are actually the same, just mathematically the same. Is that okay? So that now we use we have two ingredients. One is the one random variable or the measure function, and one sigma algebra. And we just denote such a conditional expectation by using this notation. Okay, so this is a notation of the conditional probability of A given G. And now let me just go back to this, like the example, so that we'd like to compute the conditional, either we can call it by the expectation of probability, which is this guy. So that now we fix this set, and we have the corresponding indicator of the characteristic function, and we have this G, then we should be able to calculate this one by just using this definition, because this is a mathematical definition. So what we will do is that, so because this Y is the G measurable function, so that it is able to written in terms of linear combination of two characteristic functions by using this B and B complement. And this A, B are just the numbers, just a constant. So that we can just set this measurable function by using this just a description and just plug in over here in this equation. Then once we just plug in, then all we need to just do is determine the corresponding coefficients A and B. Then if we just use this just equation and just the arbitrariness of this E, then we can get exactly number that we are all super familiar with. So what we can see is that now the ambient space should be regarded as by this set A. Then we know with this, each of these, like the values correspond to the conditional probability with respect to B and B complement. So that this Y should be written by using these numbers, then this exact coincide with the conditional probability that we saw a very long time ago. So that by using just this definition, we first recover the classical notion of the conditional probability first. Is that okay? So yeah, please let me know if this is unclear.
I don't see why you have the set A in the part that you highlighted, because I expect when you choose the lowercase a and the b as numbers, it's supposed to be chosen for the function y, so it does not depend on the capital A, right?
So this Y is assumed to be G measurable by the definition, by its definition here. And in order to make it to be G measurable over here, then it should be affected by either this B and B complement. And the empty set and the ambient set is sort of the already considered, so that it should be written in terms of the linear combination of those two characteristic functions first. And then we just plug in this expression of the Y into this equation that is this left-hand side must be equal to this guy, which is equal to this for any possible events inside of this G. So this equation from here to here should be the case for any E inside of this collection. Then now we can just plug in E to be either B or B complement. Then we will just get these numbers, simply that's it.
Then how do you get right? I'm just not sure.
Which
A
part?
is the little number A is supposed to be fixed. Now it
Yeah,
sort of
this
seems
is
like
fixed.
it sort of seems like when capital A changes, then little a also changes.
No. So up to here, these are our settings. So we fix two sets basically. We fix the set B and also set A.
Okay.
And by using this B, we created the sub-sigma algebra first. And by using this A, we created the random variable here that corresponds to this guy in this case. So A is chosen to define this measurable function, and B is chosen to define this G. And once we fix A and B both, then we consider the conditional expectation that we denoted by the conditional probability by this guy. So A and B are already fixed like the object. And then
I
we
see.
are calculating. Yeah.
I see. So A gives you X. I
Yeah,
did
A
not.
gives the measure function over here, and B gives the sub-sigma algebra over here.
I see. Yeah.
Then the corresponding AB would be determined by the classical expressions of the conditional probability that we are all very familiar with. In the case of the finite sets that Wen-Chuan today some are already calculating.
Mm.
So this is one interpretation of this mathematical definition, which looks quite like the abstract or the applied like the field, but this is actually the way to generalize the classical notion of the conditional expectation for the finite sets to the general cases. There's one explanation. Is that okay?
Mm.
And another part I also want to explain is give you some intuition and the interpretation of the way of the calculating Wen-Chuan's like the part today. So this is also one good thing to keep in for our intuition. So let us suppose now we have two random variables. So we always assume L1. Otherwise, we might not be able to apply the Radon-Nikodym theorem. That's the key reason. So that in order to define the measure by using the abstract like the integration, then we always just choose the random variables, I mean the measure functions, which are just L1 in general. So those are already somehow assumed. But now we fix two random variables, two measure functions. Then what we want to do is that we'd like to just create another measure function by adding them. Then the sigma field is defined by this guy. This notation just means that we are considering the smallest sigma field that makes this y to be the measure function. We know what those are from the measure theory, right? So that instead of using the given sigma algebra f, we first fix one measure function, y, and then we consider the smallest possible sigma algebra that makes this y to be the measure function. Meaning that we just collect all possible like the inverse image of the Borel set. And we know that becomes the sigma algebra, right? So that's the definition. And the construct this smallest one. We all saw it from the measure theory before. Do you agree? So that now we created the sub-sigma algebra here by using this y, and then now we have a one measurable function given by x plus y, and now we have a sub-sigma algebra over here, and then we'd like to know what this conditional expectation should be. So let me just repeat. So given two measurable functions, so that we create another measurable function x plus y, and by using this y, we create the sigma algebra, and then we want to calculate the conditional expectation. So that's the question in this example. Is that clear for the setting? So here's a way of the thinking. So of course, in order to know this, we must use the definition here. So all we just rely on is just nothing but this definition. That's it. But here's a way, the interpretation, how to think. So what you can see is that this x is nothing to do with this g. Do you agree? So we assume x and y are independent, and this x is nothing to do with g, whereas this y is directly related to this g. So let's just look at the correct answer. So this is the correct answer. So what this means is the following. So if we have no information of x over here, then all we can see is the expectation value. If we already have the information of this y, then we get the function itself. So that's the correct answer. So that when we take the conditional expectation, then as long as this sub-sigma algebra contains the information of that random variable, then random variable should be the outcome. Otherwise, all we get is just an expected value. And this is the way the definition really just works. So if you just try to just use the definition to just compare them, this is exactly the outcome. Is that sort of okay?
I'm not sure. You were considering the expectation, and then why is the outcome? So the outcome is still a function. It depends on.
Two parts. So the definition of the conditional expectation is just nothing but some measurable function for sure. But when we try to calculate it, so what we will get is that as long as this G contains the information of this Y, then this regular function. So by the way, the conditional expectation by this just a requirement, so it should be also linear over here. it should be linear, so that this is now equal to conditional expectation of x given this g plus conditional expectation y given g. So the linearity should hold by the definition of the conditional expectation first, so that you need to think of each like the parts separately. So what I'm saying is that if this x is nothing to do with the events over here, then all we can just say is that all we can get is just the expectation. However, as long as this y contains this is contained over here, then all we get is this y. So let me just show this part for the intuition. So suppose you have g equal to x. Okay, so let's just take the exact same one. Then what is this y? This y must be equal to x. There's not a choice.
Yeah.
But if this y is not exactly equal to x, then all we can say is that we just have some expectation. So we just get just a certain that value. That's the sort of the intuitive interpretation. Of course, we need to prove, but just justify it. But that's what I want to tell. So this x is nothing to do with this g, so that all we can get is the expected value. This y is contained in all data in this g, so that we just get the same. As we choose g equal to f, then x must be equal to y. That's the same logic.
Here, x and y are sort of chosen to be independent. They do not have the dependence like you mentioned before, like
Right.
y was the unique function, sort of like that.
Let me try to write. So it might not take too much time today. So let me just try to go over this very naive like the intuition today. So we have a probability space. We have a probability space, and we just choose two L1 functions. Okay, we just choose two L1 functions so that this guarantees that this also belongs to the same L1 for sure. This is very clear. And we create, let me just denote by this G. So G is the sigma algebra which is the smallest sigma algebra that makes this Y to be the measure function. So that it is clear that this is the sub-sigma algebra inside of given F. This is clear. So that what we want to know is this guy. This is the question. So first, I want to claim that by the definition, so what we know is that according to the definition of the conditional expectation in general, so what we know is that for any so let me just use instead of the event E, let me use the vortex B inside of G. So we know that once we take this guy, because this is still the L1 function, so that this must be equal to this guy. This is the definition of the conditional expectation. I just write the definition. Is that okay? I just write it. So if you want, let me just show you the definition again. So I just write down the definition here, and this random variable is just equal to x plus y in that setting. And I just write down the conditional expectation notation, which is this guy, into the left-hand side. And let me just share this file in the chat screen so that you can also check by yourself. So just hang on.
Oh, so that's the notation for E of
Yeah,
X.
yeah. So this looks very like the confusing for the first place. So I also totally agree with it.
Right, I see.
But let me try to, so how can I upload the file? I cannot see. Can I put the file here? I don't know. So let me just go back to just my iPad then. So yeah, just go back. So again, this is just I write down the definition of the conditional expectation. So is that okay with you? So I just write it.
Yep.
then what we know is we know the linearity, so that this is clearly okay. This is clearly okay for any B.
Yeah.
In one hand, we know that also by using the definition of conditional expectation, it is clear that we can also do this. Right? So I now just apply the conditional expected definition with respect to this guy and this guy separately. Then this must be equal. And we know that such an integrand must be unique as just Aron function by the Radon-Nikodym theorem. That is also guaranteed. So that this forces that these are the same for any B, because they are all equal as integral values. So the corresponding integrand must be unique by the Radon-Nikodym theorem. That's what we are just relying on. Is that okay? So this forces so we get this as an Aron function, because we know that Radon-Nikodym theorem guarantees that there's only one such a function.
Mm.
So that's what I said, the linearity holds inside. So in order to know this L1 function, then I just need to know each of them separately.
Mm.
Is that okay?
Yeah.
So the easy part would be this guy. So for this one, so we define the subsigma algebra G by this guy. So this G is defined to make y to be the measurable function. That's the definition.
Mm.
Then if we now go back to the definition of conditional expectation again, there's no other choice except y. This is the definition. Because in this case, this is exactly the case that f is chosen to be just a G.
Mm.
So in this case, the measure function itself should be the output. There's no other choice. However, in the case of this guy, so as we saw, so this G is nothing to do with this X. So that just we need to argue, but it's possible to argue that all we can say is that all we can just get is the just expected outcome.
Wait, what is the expected outcome again?
That just means that this just means this guy by the definition.
Okay.
So all we can get is just the expectation value for this conditional expectation part, because we do not know how to control this X by just this G. So let me just show you again. So we just need to argue in a way. So let me just now go back to the note. I'm now talking about just this guy. I'm not just talking about just this guy. So one just need to check that this is now equal to just this guy. Just this is just equal to this guy for the B chosen from this G. Then this equality shows that the rest part I needed to justify just correspond to E of X. So that all we can say is this is equal to this guy. So it's just a use the definition.
The independence of x and y, does it immediately give you that integration of x over b equals E of x times P of b?
Yeah, so as long as they are, I should say, irrelevant. So irrelevant just means that this X is nothing to do with this G. Then we just should say then, all we know is just an expectation. But if we know this Y, then we will just get the same like the random variable. So let me just, instead of just justifying, so let me just give you such an example, just one more thing. So for example, let me try to show you, should be easy to see. So suppose, let's just look at the case of the product. So given two L1 functions, X and Y, then this Y is, we assume it is G measurable, got it? In such a case, this Y, we all know from this G, so that this Y itself just go out as just a function. But we do not know the control of this X in general, so that we just need to keep this as a conditional expectation. So that's the spirit. And just the rest of it, you just need to just think by just using the definition that this is the only possible case by just using the condition. That's one thing I want to mention. And so this is already heavier than I expected. So let me just mention just one more thing. So then the notation of Wenchuan uses seems different from this, like the way of the describing the conditional expectation. The reason is the following. So what you can see is, for example, this guy. So when we deal with either the conditional expectation or the conditional probability, instead of putting the sigma algebra that we are familiar with, we usually plug in either the random variable or the measure function, right? So this is what we already somehow use. So what Wenchuan did is that, so Wenchuan plug in some values on certain random variables in the calculation you did. So, but the definition of the conditional expectation seems slightly different. So this is now defined in the following way. So given two random variables, x and y, then what we'll do is, by using this x, then we will create the smallest sigma algebra containing this x. I mean, that makes this x to be the random variable or the measure function. Then we know the definition of the conditional expectation. That's the definition of this notation. And also in one of the calculation, Wenchuan also uses the two random variables in this side. So in such a case, we consider such a like the notation. So we do not know the cardinality of index set here. We don't care. As long as we use this type of the notation, that just means that we just consider the smallest sigma algebra that makes all of those random measure functions to be the measure function. Then we just have the sub-sigma algebra G. Then we just apply the definition of the conditional expectation. Then this exactly coincides with what Wenchuan did today. So I just want to go over the definition so that so it looks quite like the abstract, but we know the rigorous now, the definition. So this is actually more convenient eventually. So that all we actually just rely on is just nothing but this equation, just this guy. That's it. Yeah, so I just felt this might be helpful. So just I wanted to share. All right, so let us just stop the record over here. I think this is a good time to stop.